Welcome to this lecture on dimension and basis. Today, we are going to explore one of the most beautiful and fundamental ideas in all of linear algebra. We will learn how to find the exact minimum number of tools needed to build an entire mathematical space from scratch without any wasteful overlap. By the end of this session, you will understand how to navigate and construct these spaces with perfect efficiency. Let us dive right in. Now that we know our goal, let us understand what a basis actually is. Imagine you are giving directions in a large empty room. You need fundamental directions like forward, right, and up. You cannot replace up with any combination of forward and right. These independent directions allow you to reach absolutely any point in the room. In linear algebra, this perfect set of fundamental building blocks is called a basis. A basis must satisfy two strict conditions simultaneously. First, it must span the space, meaning you can mix and scale its vectors to create any single vector in that space. Second, it must be linearly independent, meaning no vector in the set can be built out of the others. It is the ultimate Goldilocks set. Exactly enough vectors to reach everywhere, but not a single extra vector to cause redundancy. Building on that intuition, let us look at how we express the spanning condition mathematically. The formula you see here is the mathematical guarantee that our set can reach everywhere. Conceptually, it says that no matter which destination you choose, you can get there using your basic directions. In this equation, the symbol v represents any arbitrary vector you might pick in our entire space. The symbols v1 through vn represent the specific vectors that make up our proposed basis set. Finally, the symbols c1 through cn are scalar numbers. These are just regular numbers we use to stretch or shrink our basis vectors. If you increase a scalar, you travel further in that specific basis direction. If even one vector in the space cannot be written as this exact combination, then the set fails to span the space. Having established how to span the space, we must now ensure our set has no wasteful overlap. This brings us to the linear independence equation. Conceptually, we are asking a simple question. Is there any way to combine our basis vectors to get exactly back to the start, other than the obvious way of just not moving at all? In this equation, the right side is the zero vector, representing the origin. For a set to be truly linearly independent, the only possible solution to this equation must be that every single scalar, c1 through cn, is exactly zero. If you can find non-zero numbers that make this equation true, it means the vectors cancel each other out. That would prove at least one vector is redundant and can be built from the others, meaning the set is not a basis. Before we move on to new concepts, let us see this independence formula in action with a concrete example. We are working in a standard two-dimensional space, and we are handed a set of two vectors. v1 is 1, 2 and v2 is 2, 4. We are asked to determine if this set forms a valid basis. Since a two-dimensional space requires exactly two vectors, we only need to check if they are linearly independent. If they are, they automatically span the space. To do this, we set up our independence equation. We multiply our first vector by an unknown scalar c1, multiply our second vector by an unknown scalar c2, and set their sum equal to the zero vector. Our goal now is to find out what specific values of these scalars make this mathematical statement true. Continuing with our calculation, we need to solve the equation we just set up. We do this by distributing the unknown scalars into the coordinates of our vectors and adding them together. This operation gives us a single combined vector on the left side of the equation. For this combined vector to equal the zero vector on the right side, both the first coordinate and the second coordinate must individually equal 0. This creates a system of equations that we can solve. Let us isolate the relationship for the first coordinate, which gives us c1 plus 2 times c2 equals 0. By looking at this specific equation, we can start to see if our scalars are absolutely forced to be zero or if other possibilities exist. Now, let us finalize our check. By moving the C2 term to the other side of our equation, we see that C1 is exactly negative 2 times C2. This is a crucial discovery. It means that our scalars do not have to be zero. For instance, if we simply choose C2 to be 1, then C1 becomes negative 2. If we substitute these chosen values back into the original equation, negative 2 times the first vector plus 1 times the second vector equals exactly 0. Because we found non-zero scalars that make the equation true, the vectors are linearly dependent. Physically, one vector is just a stretched version of the other. Therefore, this set is not a basis, as it just repeats the same direction twice and cannot span a two-dimensional space. Now that we have seen how to check a basis, a fascinating property emerges. Once you find a valid basis for a space, every other possible basis for that exact same space will always have the exact same number of vectors. You might choose a completely different set of fundamental directions, but the total count of those directions will never change. This universal count or cardinality of vectors in a basis is called the dimension of the vector space. For example, a flat plane always requires exactly two basis vectors, so its dimension is 2. If you try to use 3 vectors for a plane, one will always be redundant. If you try to use just one, you will not be able to reach every point. The dimension is a fundamental, unchangeable property of the space itself. This brings us to the mathematical definition of dimension. Conceptually, this simple equation represents the profound truth that the size of a basis is locked to the space it describes. If we have one basis with m vectors and another completely different basis with n vectors, this formula states that m must equal n. Here, m is the number of vectors in the first basis and n is the number of vectors in the second basis. Because these two counts must be exactly equal, we can define this unique, unchangeable number as the dimension of the space, written mathematically as dim v equals n. If the dimension increases, the space becomes more complex, requiring more fundamental directions to navigate it. Now that we have stated this formula, let us understand where it comes from, by proving why any two bases must have the same number of vectors. We start by supposing we have a vector space V. Let us say we have one basis called B1 containing n vectors and another basis called B2 containing m vectors. Because B1 is a basis, it spans the space. This means every vector in B2 can be written as a combination of the vectors in B1. If we take one vector from B2 and add it to B1, the new set is now redundant or linearly dependent because the new vector is just a combination of the old ones. To fix this, we can remove one of the original vectors from B1 to restore independence, effectively swapping a vector from B2 into B1. Continuing our proof, we repeat this swapping process one by one. Each time we bring in a vector from B2, we must kick out a vector from B1 to keep the set independent and spanning. Now imagine if m, the number of vectors in B2, were greater than n. We would eventually run out of vectors in B1 to kick out. This would leave us with extra vectors from B2 that are linearly dependent on the ones we already swapped in. But this contradicts the very definition of B2 being a basis, which must be completely independent. Therefore, m cannot be greater than n. By reversing the roles of the two bases, we use the exact same logic to prove that n cannot be greater than m. The only logical conclusion is that m equals n. So, we have proven that dimension is fixed. This brings us to a practical question. How do we actually build a basis if we are just handed a random pile of vectors? There are two main methods, depending on what you start with. The first method is called shrinking a spanning set. If you have a large set that covers the whole space but has too many vectors, you test them one by one and throw away any vector that can be built out of the others until only an independent core remains. The second method is extending an independent set. Here, you start with a small group of independent vectors that do not yet span the space. You look for a new vector that cannot be reached by your current set and add it in, repeating until the space is fully spanned. Both methods guarantee a perfect basis. Before we calculate anything, let us see this shrinking method visually. Look at the diagram on your screen. We are in a two-dimensional plane, defined by the horizontal x-axis and the vertical y-axis. We started with 3 vectors, which we know is one too many for a 2D space. You can see 2 blue vectors, v1 and v2, pointing along the axes. Then there is a red vector, v3, pointing diagonally. Because this red vector can be reached by simply combining the 2 blue vectors, it offers no new fundamental direction. It is entirely redundant. By identifying this, we can safely cross it out, as shown by the large X. The remaining 2 blue vectors are independent and span the plane, forming our perfect non-redundant basis. Now that we have seen the visual intuition, let us try constructing a basis using the shrinking method with actual numbers. Suppose we are working in a standard 2-dimensional space. We are given a spanning set consisting of 3 vectors. v1 is 1, 0, v2 is 0, 1, and v3 is 2, 3. Our task is to reduce this oversized set down to a proper basis. From our earlier proof, we know that a 2-dimensional space has a dimension of exactly 2. This means any valid basis must have exactly 2 vectors. Since we currently have 3 vectors, we know for a fact that we have one redundant vector. We need to identify a way to express one vector as a combination of the others, so we can remove it. Let us finish shrinking our set. By simply looking at the coordinates of our vectors, we can see a clear relationship. The third vector, 2, 3, can be built perfectly by taking 2 of the first vector and adding 3 of the second vector. This mathematical statement proves that the third vector offers no new directions. It is entirely redundant. Because it is redundant, we remove it from our set. We are left with a new set containing only the first 2 vectors. These 2 vectors, 1, 0 and 0, 1, cannot be built from one another, so they are linearly independent. Since we now have exactly 2 independent vectors in a 2-dimensional space, they form a perfect Goldilocks set. We have successfully constructed a valid basis. Now that we have mastered the math, let us understand why dimension and basis are absolutely critical in almost every field of modern science and engineering. Think about computer graphics. A basis defines the entire 3D world your video game character moves in. By simply changing the basis, the computer can rotate and scale complex objects instantly. Or consider data compression, like saving a photo as a JPEG on your phone. Engineers use a special mathematical basis to identify which parts of the image are essential and which parts are redundant. By throwing away the redundant data, they save massive amounts of file space. Without the concept of a basis, we would waste enormous computing power processing redundant information. A basis gives us the most efficient, streamlined version of reality possible. We have covered a lot of ground today, so let us summarize the most important ideas. First, remember that a basis is the ultimate Goldilocks set. It spans the entire space, so you can reach anywhere, but it is linearly independent, so there is absolutely no redundancy. Second, we proved that the dimension is a fixed, universal property of a space. Every basis for that space will always have the exact same number of vectors. Finally, we learned that you can actively construct a basis by either shrinking down an oversized spanning set or extending a small independent set. You now have the fundamental tools to measure and navigate mathematical spaces efficiently.
Great job following along with these core concepts of linear algebra.